Hi, I'm Santiago and I'm from Intel Labs, and today I wanted to talk to you about safety-aware reinforcement learning, or SARL. So we're basically interested in investigating the idea of safety in reinforcement learning. If we think about RL agents being deployed in actual real-world scenarios, the importance of safety becomes fairly obvious in the sense that when you're deploying an agent in any type of environment, you don't want it to cause undesired side effects, whatever they may be. And because it is so important, researchers have already started to develop platforms that you can test your ideas on. So one of those platforms for RL environments is DeepMind Safety Grid Worlds, which you see an example of here. And another one is OpenAI Safety Gym, both of which allow you to create these test beds to investigate different safety scenarios. Now, a common problem with many of these test beds is that they're very specific to what the designer wanted them to be. And also, many of them have difficulty approximating dynamical systems. And we were interested in coming up with an approach that did not have the limitation of overfitting to that particular environment or any particular task, and that can also work in dynamical systems. Because of that, we decided to focus on SafeLife. SafeLife is essentially a suite of environments that allows you to generate a lot of different patterns just based on three simple rules that are written on the slides. Every cell is either alive or dead. Live cells die unless they have 2 or 3 neighbors, and dead cells stay dead unless they have exactly 3 neighbors. So even with these simple rules, you can already see on the top left, you can create patterns that take on a life of their own, and that's what makes many of these setups interesting. Within Safe Life, we have the option of generally doing 2 tasks. The Prune task is this one shown right here, in which you're trying to remove these red cells. And while the agent is removing the red cells, you can see that it's causing side effects already, and that is kind of what we want to avoid. So ideally, we would want the agent to remove the red cells without causing any disturbance to the green patterns. Another task that we can do is called the Append task. So here we're trying to fill in the blue cells, and we're again trying to do it without disturbing the environment, which the agent is not doing in this video. Now, our approach was to assume that we have a distribution that represents the task behavior that they want, and a distribution that represents the safe behavior that we want. Once we have those two distributions, we can essentially take a distance between those distributions, and we can use that to regularize our RL objective. And that is shown in the first equation here, and then we can backpropagate the gradient through it and end up with the updates that we need for our engine to be actually trained. Now, the good thing about this is that both of these distributions can come from essentially anywhere we want them to come from. So the task distribution, commonly you will train the RL agent directly to give you that. And in the safety distribution, you can substitute that for whatever you like. In our case, what we did is we just trained an RL agent on the side effect metric that was given by SafeLife. And our experiments, they showed that this method is competitive with a reward penalty baseline, where basically you subtract a side effect from the reward that is shown in the original SafeLife paper. And on top of that, we get the benefit of the zero-shot generalization, which is what I mentioned earlier, that you can just drop in your safe distribution from wherever you want. So in this case, what we did is we trained an agent to give us a safe distribution from a task different than what the primary task agent was solving. And we saw that without any type of retraining, that sort of generalization can happen.